Last time we focused on inelastic collisions, in which we said that the linear momentum is conserved but kinetic energy is not conserved. So this week we're going to derive the equations for elastic collisions in which both linear momentum and kinetic energy are conserved. Alright, so always remember that linear momentum is conserved in every single case. But kinetic energy is only conserved if we're working with elastic collisions. And it's very rare to see elastic collisions in the real world because there's always going to be some transfer of energy or loss of energy, kinetic energy, to, for example, thermal energy. If you have a collision, if there's sound from the collision, then that kinetic energy has been transformed to some other type of energy. So just keep in mind that elastic collisions are pretty rare in everyday life. But for the purposes of testing our own knowledge and exercising our familiarity with these concepts, we're going to be working with fictitious elastic collisions. All right, so we know that linear momentum is always conserved. So we're going to write the equation for conservation of linear momentum, which says that the sum before and after are the same. All right, now we have another interesting case where kinetic energy is now conserved as well. So we can go ahead and write the equation for the conservation of kinetic energy, which says that the sum of the kinetic energies before and after are equal. So now we have two equations, and usually you will be given V1 naught and V2 naught. These are your initial conditions that you will usually know. So now we have two unknowns, V1 and V2, and two equations. So we can solve for these equations. And it might look a little bit tedious right now, and I will say that it is kind of tedious, but once you do the math one time, you'll be able to do it many times after. So if we notice in the kinetic energy equation, we can cancel out all these 1/2, right? So we're left with m1 v1 naught squared plus m2 v2 naught squared, and so on. And then we can rearrange this equation to bring all the m1 terms to one side and all the m2 terms on one side to get something like this. So we have m1 v1 naught squared minus m1 v1 squared equals m2 v2 squared minus m2 v2 naught squared. So this is just rearranging the equation. And then if you remember, we know that a squared minus b squared is equal to a plus b times a minus b. So we're going to do that here. We're going to bring the masses out and then use the property that I just mentioned to get this new equation over here. And then what we're going to do after we get this equation is we are going to go back to the linear momentum equation. Let's bring that down here and also rearrange so that all the same mass terms are on one side. So we know that m1 v1 naught minus m1 v1 equals m2 v2 minus m2 v2 naught. And again, we are going to distribute the masses out to get that m1 times v1 naught minus v1 equals m2 times v2 minus v2 naught. And we'll notice that this term we have found in our reduced kinetic energy equation as these terms right over here. So we know that those red terms are equal to each other, which means we're bringing it all down here, which means that the remaining terms must also be equal, which tells us that v1 naught plus v1 must equal to v2 plus v2 naught. And that is going to be a key equation for elastic collisions. All right, so now that you have those relationships between the velocities, you can start rearranging and substituting them back in to your linear momentum equations to find the final values for v1 and v2, assuming that the problem has given you v1 naught and v2 naught. Or vice versa, if they're giving you certain values for v1 and v2, you can also find v1 naught and v2 naught. So that is how you derive the equations for elastic collisions. I hope this was helpful. I know it's a bit tedious, but it will get a lot easier as you do it more. So I hope you guys have learned something new, and I will see you guys in the next video.